Welcome to question C3 in the higher level 2020 paper. It's a structural forms question. The image on the right shows an air traffic control tower in Newcastle Airport. It includes a hyperboloid of revolution and 3 truncated cones. Okay, so we've got our hyperboloid of revolution, truncated cone at the base, truncated cone at the top, and I suppose the area people will be viewing from is also a truncated cone. We can see then here as a hyperboloid of revolution and 3 truncated cones. The projections of a model of the tower are shown in C2. Okay, so here's our projections. Curve LMN, so LMN, so just that part is, and L1, N1, N1 are branches of a double hyperbola with vertices N and N1. So here and here are our hyperbola. Right, the rest then is going to be our truncated cones. The asymptotes A, B and CD are up to the double hyperbola are shown in elevation. So we've got AB and CD also there. They are asymptotes. Draw the given elevation or plan and elevation. So to guide us through the question, draw the plan first. Okay, so we've got a scale 1 is to 200. I've converted all the measurements there, but just to go through, I don't know, for the top one here, 20 meters, okay, is equal to 2,000 centimeters, which is equal to 20,000 millimeters. Okay, and we deal in millimeters. Okay, so I just multiply by 100 to find out how many centimeters, multiply by 10 to find out how many millimeters. And we're going to scale 1 is to 200, so let's divide that by 200. Okay, and into that goes 100 millimeters. Okay, so 20 meters is equal to 100 millimeters that we'll be using to measure it. And I've converted all the rest of those. You do the same before you begin the question. So let's start out by drawing the plan. I've got the diameter of all of these circles. Okay, some truncated, some of them represent truncated cones, and others the hyperboloid of revolution. But we'll draw them all to start with anyway. And we've got our diameters running down along there. So here's my XY line. Just make sure I've got enough space for everything. So we'll put center approximately there. So large circle is diameter 24, which is diameter 120 really, so we'll set our compass to radius 60. Now we've got diameter 20, which is 100, so 50 is our radius. We've got 16.8, which is 84, so 42. We've got 10 meters, so that's 50, so radius 25. And that is representing our throat circle. Let's see it in detail there. Okay, and if there's one of those circles they haven't given us a diameter for, but if we follow up along here, we will actually get a measurement for it in the end. So we'll come back to that in a while. Okay, so let's project up into our elevation. They've given us heights and elevation. Let's step off those heights also. So we've got 6 meters, which is 30 millimeters, and 120, which is, 12 meters, which is 60 millimeters. 6 meters again, which is 30. 3.6 meters, which is 18 millimeters. And 3 meters, which is 15. Truncated cone here. Bottom. S right there. S N N1 N is here, N1. So you can see things a little clearer. There. So N and N1 are actually in here on the throat circle. So N1 and N. Okay. Looking at the rest of this, we don't have the width here of that, or the diameter of that top part, but we can see it's in line with L and L1. Okay, and we also don't have the radius of L1, do we? No. So what we're going to do is we're actually going to continue on. We'll come back to this at the end, and we're going to draw a portion of the double hyperbola, and once we can draw one side here, we'll be able to mirror it up and get position of exact position of L and L1 and project up there. So let's get on with that. Okay, so my asymptotes are going to be touching off the throat circle, so here they are. extend them up and find the position of an elevation, and go through center point. Okay, so those are my asymptotes. And now I'm going to pick points, just random points along it. Random points along my asymptotes in order to draw the hyperbola. So 1, 2, 3, 4. 4 should be loads. Rotate them around, so to the position of C, our hyperbola shape. So now we can project those up. Index them 1, 2, 3, 4. Okay, and let's project them onto the asymptote. They're on the asymptote here, 1, 2, 3, 4. So let's project them onto the asymptote and then across. So this is like taking horizontal cuts of our hyperbola. So 1, 2, 3, 4. Point. These positions. 4. Okay, so that is giving me a portion of our hyperbola shape. Okay, and I can mirror that up, okay, or not mirror, use axial symmetry to project that up. So, using this as my axis, point. Okay, so got those running up. So where these lines, so I'll just draw it lightly to begin with, just to show you what I'm doing. So we know the position of L is going to be along that height line, okay, that distance there, down from S, okay, and I have that line marked. Now I've located my hyperbola running up through that height, so right there where they intersect, that's going to be my line L, and that will help me find L on the opposite side, and in turn the position of the top points there and the width of the radius that we need in elevation. So put those in heavier there. So that now is L. Okay, and now I can use axial symmetry to find everything on the opposite side again. So project everything across. exact position of L1 brought over also. So that's my L1. And join L and S. Okay, so now let's project up the height of L there and L1, or the position width of L and L1. And we can see here that if I go from Q in the center out up to that point, that will give me that position or that line. So it's quite a bit in this question now. Okay, I can also bring that radius down. So I could either just take it from my elevation here, right, but also brought it down, and there we have okay. So next up, that's our plan and elevation drawn. Now I want to determine the directrices and focal points of the double hyperbola. Okay, so here's our double hyperbola. What we want to do, we've got our asymptotes running through. What we want to do is draw an auxiliary circle, which is that radius, and where that auxiliary circle intersects my asymptotes. Auxiliary circle drawn. Okay, and here's my asymptote coming up. So where it intersects the asymptote, and intersects the asymptote here, here, and here. I'll just extend on my axis. So I need to draw lines at 90 degrees to the asymptote from where the auxiliary circle hits that back onto my axis. Actually, I'll set it this way, save time, back there, so that's the focal point. If you wanted, you could project them back from here as well, but that is going to be my focal point there. F and F. And F1. Okay, so it's just a 90 degree angle. Okay, so I think that's everything. Let me just label up my A, C, and D, B. That's everything I need. Okay, then we want to, the line PQ represents the flight path of an aircraft. So P to Q, P to Q there. Draw the projections of the line PQ and determine the length of the shortest perpendicular distance from point S to line PQ. Okay, so what I'll do first of all is I'll draw the projections of that line PQ. So we've got P is out, worked that out earlier, it's 100, straight up horizontally across from S, and it'll be horizontal across from S. So that's something I'll be able to use. I'll talk about that in a moment. Horizontal across from S, that is point P. Let me just label S. S and Q is down here. P to Q, Q, P to Q. Okay, Q. So, essentially we need to draw the plane PSQ and then find the perpendicular distance, or draw the perpendicular line then from S to that line PQ. Right, starting off, if I want to draw the true length or true shape of that plane, I need the true length of each edge. Okay, line PS is a horizontal line. So when I look down on top of it, okay, that is going to be a true length line from P to S. So that's one already determined. Okay, the line SQ, right, is a sloping line, so you can imagine it's sloping there out towards us in elevation, and it's sloping down away from us there in the plan. So I'm going to rotate that line around so that when I see it in elevation, that's going to be a true length line. So I'll do that first. So I'll determine the true length of that. Okay, so that then is a true length line. Okay, and then we need to determine the true length of PQ. So I'll do the same thing with PQ then. I'll rotate the thing, just go through it again. It's sloping out towards us here, and it's sloping down away from us. So same thing if I rotate it around so that I'm looking perpendicular to it. That's probably the best thing. PQ. Check that up. So that is another true length line, PQ. So what I'll do now is I'm actually going to get that distance PQ on my compass. And swing it from P somewhere out here. Yeah, because PS is a true length line, I have one. Now I'll have a true length line running to PQ, creating my new PQ, and then I can get my true length of SQ and swing that from S. Okay, that is done now because it has created a plane. PQS. Great. And then what they're looking for is the perpendicular distance, determine the length of the shortest perpendicular distance. So let's go using sliding set squares. Slide back. And the length of that then I've got as 47.5 meters. Okay, and if you wanted just to be sure, you can convert that then into meters. So work in reverse. So let's just here for that. So it's at 47.5 millimeters, and if we convert that, so multiply that by our scale, which is 200, so that gives me 9,500, which is 9.5 meters. Okay, I'm sure in the marking scheme it's not required to do that, but there's no harm in doing it, doesn't take long. Okay, so that was the section C, question C2, structural forms question in 2020. A fair bit in that, particularly in that part C, a lot of problem solving involved and linking back to planes.